Hello students, today we'll study second law of motion. Okay, and in this chapter force and laws of motion, already we have studied first law of motion. So just memorize those that law, that if one body is at rest and if you are not applying any external force, then the body will not move. If it is in the uniform motion, then it will be in uniform motion if you are not applying any external force. Now here, in the second law of motion, we will discuss regarding the inertia and then we'll discuss regarding the momentum. Okay. So, just a minute. Here, second laws of motion that I have told you that this will be discussed here. So first thing is the inertia. Now what is inertia? So here in this picture you can see that one bucket you have that is empty. So this is our empty bucket and this is filled with the sand. So according to the mass, you can find out that according to this will be heavier than the empty one. Fine. So all the objects, those have a tendency to resist the change in that state of motion or rest. That means if any object in rest is in rest, then it has a tendency to resist the change of its state. Similarly, if one object is in motion, then it has a tendency to resist the change of the state. That is the motion state, right? And this tendency is called the inertia. So, just a minute, I am taking the highlighter. This tendency is called the inertia. Okay, this is called inertia. So all bodies do not have same inertia because the inertia that depends on the mass of the body, and mass of the body or object that is not same for every object, right? So if more mass, then more inertia. So this is very important, that what is the relationship between your mass and the inertia. So if you have more mass, then you have more inertia. More inertia. So you can see that if you have a table that is the weight of the table is, mass of the table is very high, or a block, the mass of the block is very high amount, at that time you can see that it is very hectic to pull that one, right? That means what? The resistance, how much it offers to the person, that is very high. So if mass of the object is very high, at that time you can see that the inertia, it is also very high. Or I can say in other way that if inertia is very high, that means the mass of the object, that is also very high. Okay. Here, if someone wants to pull this empty bucket, then you can see that it is very easy to pull this one, but it is very easy with respect to this one, with respect to this sand filled bucket. Okay, so here the mass of this sand filled bucket, that is very high. Here the mass is very high, and here that is high, and here empty. So that's why the mass of this bucket, that is low. Okay, small amount of mass you have here because it is not filled, it is empty. So that's why the mass of this bucket, that is low. That's why inertia is low. But here the sand filled bucket that has the mass very high, so the inertia, that is very high. That means the resistance, the tendency to resist the change of state, that is also very high. Okay. So here, an athlete does not come to rest immediately after crossing the winning line due to the following 4 points are there, and 1 point will be your correct answer. So one athlete is here. Now this situation actually you can see whenever you are participating in any race, whenever you have the sports competition in your school, right? So here one athlete does not come to rest immediately after crossing the winning line. So here you can see that if this is the finishing line, if this is the finishing line, and these are the tracks, and these are the tracks of the person or the athlete, these are the tracks, and this is the finishing line, and here you can see that the athlete will run through this track, and whenever the finishing line is here, the athlete will be in a motion after the finishing line also. It is not possible for one athlete just to stop at the finishing line suddenly. It is not possible. So why this is? First point, inertia of the motion, inertia of the rest, inertia of direction, and none of the above, right? So here I have told you the tendency, inertia is the tendency of the object to resist the state of it, right? So here the athlete is in the motion, right? Because he or she is running in this track, that means he or she is in motion. So the inertia here, that means it will resist the athlete to stop, because the change in the state here from motion to rest, from motion to rest. So the athlete here, the athlete does not come to rest immediately after crossing the winning line, that means the finishing line, due to the inertia of motion. Inertia of motion. Next, inertia is the property of the body by virtue of which it cannot change by itself. Options: its state of rest, its steady state of uniform motion, its direction of motion, all of these. Now, inertia is the property, obviously, if one object is in rest condition, then it is the tendency to resist the change of the state, that is the rest condition. If any body or object is in the uniform motion, then it will resist that change of state, or it will resist the direction of motion. So that's why the proper answer is the all of the above, right? Now, when we stop paddling, the bicycle begins to slow down. And this is because of the first one, the frictional force acting along the direction of the motion of bicycle. That means here, suppose the bicycle is moving in this direction, then always there will be some frictional force in this direction. Frictional force, that means that will resist the bicycle's tire, right? So here the frictional force acting along the direction of the motion of the bicycle, that is not okay, because here I have shown already, if bicycle is moving in this direction, the frictional force will be acting in this direction. Now, air resistance which is in the direction of motion. Air resistance which is in the direction of motion. Now, this cannot be an answer, because the air resistance, the bicycle, it has a big size. So here air resistance is not so much effective here, because now you want to stop the bicycle. Then frictional force acting opposite to the direction of the motion of bicycle by the road. Whenever you are paddling, at that time also the frictional force is acting. So, and fourth one, that is the nature of the bicycle to stop after some time. So this will be the correct answer. Okay. Next, the second law of motion. First, we are just going through one term, that is the momentum. That is the momentum. Okay. Here, momentum means impacts produced by objects depend on their mass and velocity. Okay, so momentum of an object that is defined as the product of mass and velocity. So this one is our momentum, and momentum that is represented by P. This is our momentum. Just a minute. Let me take the pen. So here P is the momentum, M is the mass of the object, and V is the velocity of the object. Okay, so momentum is defined as the product of mass and velocity, and obviously it is the product of mass and velocity. Velocity here, this is a vector quantity, so momentum is a vector quantity and it has direction as well as the magnitude. Vector quantity means we know that it has the direction as well as the magnitude, so we are calling this is the vector quantity. Okay, so the momentum is that impacts produced by the object depending on their mass and velocity. Next, the second law of motion. Here, the rate of change of momentum, of an object is directly proportional to the applied unbalanced force in the direction of the force. Here, delta P, this is change in momentum. Okay. T is the time, M is the mass, V is the final velocity, U is the initial velocity, and A is the acceleration, F is the force. Okay, so remember this thing. Here, the rate of change of momentum. Rate of change of momentum is the delta P by T. So with respect to time, how much is the change in momentum? This is the delta P by T. So this delta P by T, rate of change in momentum, that is proportional to force. That means this delta P by T, rate of change of momentum, that is proportional to MA, mass into acceleration, because here force equals to how much? Force equals to M into A, right? So here you can see that, or we can write down that is proportional to M into acceleration is V minus U by T. Final velocity minus initial velocity divided by T. This is our acceleration. So it is proportional to M into V minus U by T. So that's why it has been written here, the rate of change of momentum, that is delta P by T, proportional to M V minus U by T. Or that F is proportional to MA, or I can write down that F is proportional to K into MA. Now what is K? This is a constant and it depends on the amount of force, mass and acceleration. Generally, this K equals to 1, and it is defined if you are applying 1 unit of force on 1 kg of mass with the acceleration of 1 meter per second square, then the value will be K equal to 1. Value of K equal to 1, right? So this definition of this K is what? I am applying 1 unit of force to how much mass? 1 kg of mass. How much acceleration? 1 meter per second square acceleration. So at that time, this constant, that will be your force divided by M. Okay. So this is the second law of motion. The rate of change of momentum of an object is directly proportional to the applied unbalanced force in the direction of the force, right? Now, let's see this thing. Just a minute. If the mass of the body is doubled, okay, wait, I have chosen the different thing. I require this one. So if the mass of the body is doubled, that means what? Previously the mass was m, now it becomes twice m. And previously the velocity is v, now it becomes v by 2. Okay, then linear momentum of the body will be how much? Now always you know that the momentum that is already related to the mass and velocity, right? And the momentum that is product of mass and velocity. Now this is the previous one. Now the new momentum, suppose I am writing p dash. So the new momentum, that is twice m, into the new velocity, that is v by 2. So these two will be cancelled. That means it will be mv. So we can say that p equals to p dash. P equals to p dash. That means what? The momentum is same. So it is remain same, right? So if the mass of the body is doubled, velocity become half, then also the linear momentum of the body will be same. A water tanker filled up to 23 of its height, is moving with a uniform speed. Fine, it is in motion, uniform speed. On a sudden application of brakes, the water in the tank would, what will be the right answer? Move backward, move forward, be unaffected, rise upwards. Now here it will move forward due to the inertia. Okay. Now conservation of momentum. So already you know that what is momentum? It is related with the mass and what will be the velocity. Fine. So here the conservation of momentum is a major law of physics which states that momentum of a system is constant if no external forces are acting on the system. If no external forces are acting on the system. And it is a little bit derived from the Newton's first law. The total momentum of an isolated system is conserved. Isolated system means net external force on the system is 0. Now, let me take another color. Suppose this is a system. Okay. This is a block. This is a block. In this system, you are applying the force F in this direction. And in this direction also you are applying the force. That means the net force F net, that equals to F minus of F, that is 0. So this is called isolated system. Net external force on the system is 0. Suppose I am applying force here F. I am applying also force here F. At that time also your net external force on the system is 0. Right? So conservation of momentum, that states the momentum of a system is constant if no external forces are acting on the system. So conservation of momentum, it states what? It states that the momentum of the system is constant if no external forces are acting on the system. Right? So here, if all the forces will be nullified, that means no external forces actually I am applying, right? So here it is an isolated system. Now, in the conservation of momentum, two things are very important. First one is the concept of system. Second one is the environment. What do you mean by environment and what do you mean by system? Now, system means the part of the universe chosen for analysis is called system. Like in the previous slide, you have seen that one block I have taken where I have applied some external forces. So this block is the system, right? And suppose I am taking one car. So if the car moving with a constant velocity, it is a system. And all the forces within the car are internal forces, and all the forces acting on the car from the environment are external forces like friction. Similarly, for the block also, suppose this is the block and this one is the ground. This one is the ground. And here, you know that in this direction, always there will be frictional force. Frictional force. Okay. If you are applying external force in this side and frictional force already will be acting in this side. So this frictional force is an external force. This F is an external force, right? So that means this belongs to environment, and system is what? This block is the system. So this is the system. Now, this is very well known to you. Application of law of conservation of momentum. Now, in your daily life also you are using this conservation of momentum. Also in rocket science we are using this. Now, the conservation of momentum we are using for space travel. We are using for space travel. Just a minute. We are using for space travel. Now, here there is no medium in space to exert a force, but the rockets that will travel. So whenever the rocket will be launched, at that time you can see that it will eject matter at very high speed, So is in an isolated system, the momentum should remain constant. Therefore, the rocket will move in the opposite direction with the same momentum as that of exhaust. So here you can see that whenever the rocket will launch, at that time you can see that here the rocket will eject the gases here with a very high speed. And what it will do, actually this force, here you are applying this thing. Now, according to the conservation of momentum, that will be balanced. That means that will be constant. So what it will do, the velocity, it will move in this direction with a high velocity. Because this gas, CS material, this gas that will be ejected from here with a very high speed. Okay. And to maintain the conservation of momentum, the rocket will move with a very high velocity but in opposite direction. Okay, so that's why we are using conservation of momentum in case of rockets also. Let's solve some MCQs. The masses of two bodies are in ratio of 5:6 and their velocities are in ratio 1:2. Then the linear momentum will be in the ratio of how much? So it will be our how much? Here, I'm just writing one thing. Let me select just a minute. In color. Fine. You know that the momentum. Okay, I have to find out the momentum. Now, the mass of the two bodies, suppose M1 and M2. The mass of these two bodies 5:6. Right? And the velocities, suppose V1 and V2. These velocities are 1:2. Now, what is the momentum? Product of these two? Right? That means the product of 5 and 1 So 5 and the product of 6 and 2, 12. So the result is 5:12. Okay. Which of the following is not an application of conservation of linear momentum? So that is not following the application of conservation of linear momentum. First example they have given us, while firing a bullet, the gun must be held tight to the shoulder. Number 2 or B, when a man jumps from a boat to the shore, then a rocket explodes on midway from the ground. A body suspended from the hook of its spring balanced in a lift, which is accelerated downward. So here the conservation of linear momentum will be applicable. You know that the rocket explodes on midway from the ground. Here, the rocket. Okay. So Newton's second law, here it states that acceleration of an object that depends upon two variables. One is the net force acting on the object, another is the mass of the object, right? So here the Newton's second law states what? The acceleration of an object depends on two variables, net force, also the mass. So the acceleration of a body is directly proportional to the net force acting on the body and inversely proportional to the mass of the body. So here the acceleration, just a minute. So here you can write the acceleration that is proportional to your net force and acceleration is inversely proportional to the mass. Okay. So acceleration of the body is directly proportional to the net force acting on the body and inversely proportional to the mass of the body. Okay. Here we can see this thing. This is a figure where we will derive the Newton's second law of motion. Here you can see the car where time, t is the time, x is the distance, and m is denoted by mass, v is denoted by velocity. Okay. So at time t0, the car is at distance x0, having the mass m0 and velocity v0, where this car mass is m1, velocity is v1, x1 distance and t1 is the time. So deriving the Newton's second law, force that equals to change of momentum with change of time. So that is change of momentum with change of time. Okay. So if we write the difference form, then we can write the force that equals to m1 v1 minus m0 v0 divided by what is the time change in the time, t1 minus t0. Okay. Now if we consider constant mass, so if with constant mass m, we can write down F equals to m into v1 minus v0, this divided by t1 minus t0. Okay. And force equals to, you know that, mass into acceleration. Mass into acceleration. So here the net force whatever applied, that you know that that equal to mass into, this is the V1 minus V0 by T1 minus T0. This is the acceleration part. Okay. Next, here you can see that always I am telling net force and net force. In the previous lecture also I have described. Now again I am just describing this one. Here you have one horse. Suppose 20 Newton, that much force has been applied in this direction and 30 Newton in the right direction. Okay. So two forces of the magnitude 30 Newton and 20 Newton are exerted to the right and left. So if net force you have to find out, that means your 30 Newton minus 20 Newton. So 10 Newton force will be applied to the right side, to this side. Okay. Now application of the second law. I have told you whatever the first law, second law and third law also we'll study. All these laws always we are using in our daily life, but we are not noticing all those things, and sometimes we know the explanation in terms of physics, sometimes we do not know the explanations in terms of physics. Now after this lecture, whenever you are just facing your daily life activities, at that time please try to search which law has been applied there. Okay. So in the Newton's second law, if you are kicking a ball, when you are kicking a ball, that means this boy, this sweet boy, here you can see that he is kicking the ball. So here he will exert a force in a specific direction, this direction, in a specific direction. The stronger the ball is kicked, the stronger the force will be put on it, and the farther away it will travel, right? So Newton's second law is applied to identify the amount of the force needed to make an object move or make to stop. So here the ball, suppose it is in the rest condition. Now this boy applied a force here, and this boy applied a very high force. So the ball here, you can see that it is now in motion. Okay. So due to this stronger force, the ball will travel. Here the pushing a cart, you can see that another nice boy here. So here, suppose you have empty cart, at that time it is very easy to push. But if you have loaded cart, at that time you can see that it is a little bit hectic to push because of the mass. So more mass requires more acceleration, and here you need to apply more force to push the cart. This you can see whenever suppose you are going to any shopping mall, or you can see that some your guardians also they are going, and you along with you they are buying a lot of things in the first of month. At that time you can see that whenever the cart is loaded, at that time it is very big to push that thing. So because it is loaded, that means loaded means the mass is very high. Okay, so the mass is very high. Now here two people are working. Always this is a fatty people, and this one very slim people, very good. So here the speed of this person, B person, this speed of this person is low, because the mass of this person, this weight of this person is very heavy, heavier than the A person. So he will walk slower than the person A. So that means the acceleration of the person weighing lighter is greater. So acceleration of this person will be higher. Okay. Okay. Now if try to solve this one, if there is a block of mass 2 kg, always I have told you, first you have to write down the given data. Just a minute, I'm just changing the ink color. So mass 2 kg and force here 20 Newton, here it has been given 30 Newton. So net force that is the 20 Newton minus 30 Newton minus 10 Newton. So acceleration equals to F net divided by mass. So this will be divided by mass is 2 kg. So this will be 5 meter per second square. Okay. So that means the acceleration is 5 meter per second square. And here you can see that the force of 30 Newton in the negative x direction. So you can see that in this direction, if you have the force much, so your acceleration is minus 5 meter per second square. Next, how much horizontal net force is required to accelerate a 1000 kg car at 4 meter per second square? Fine. Let's solve this problem. You know that F net force is the mass into acceleration. Now, given data that is mass is the 1000 kg, acceleration that is 4 meter per second square. So F net that will be 1000 into 4, that is 4000 Newton. And this is the answer. Okay. Now, how does Newton's second law of motion apply to rockets? Already a little bit we have discussed. So if this question will come in your examination, then you have to write down, according to Newton's second law of motion, we know that the force is product of mass and acceleration. When a force is applied to the rocket, the force is termed as thrust. And greater thrust, greater will be acceleration. So acceleration is also dependent on the rocket's mass. The lighter of the rocket, faster will be the acceleration. Actually, what happens whenever you are just launching the rocket, some gas will be ejected from the rocket. So this has a very high speed, and that to conserve the momentum, you can see that it will accelerate. But obviously, the mass is a factor. If your rocket has very small mass, at that time you can see that the acceleration is very high. Now, how does Newton's second law apply to car crash? According to the definition of the Newton's second law, what is this? Force is the dot product of mass and acceleration. Just a minute, I'm taking the different color. So here you know that force, that is the mass into acceleration. Okay, dot product of mass into acceleration. Now the force in a car crash is dependent either on the mass or acceleration of the car. So as acceleration or mass of the car increases, the force with which a car crash takes place will also increase. Now generally what happens in the car crash, the acceleration is very high. At that time the force is also very high, so that here you can see that the crash, this whenever it will occur, at that time the force will be very high because the acceleration is very high, right? Now, what is the other name of the Newton's second law? The other name of the Newton's second law is the law of force and acceleration. Now, what does the law of conservation of momentum state? Now, here you have to say the law of conservation of momentum statement. It states that in an isolated system, the total momentum of two or more bodies acting upon each other remains constant unless an external force is applied. Okay, the momentum can neither be created nor destroyed. Neither be created nor destroyed. The law of conservation of momentum is based on which law of motion? This is the next question. Okay, The law of conservation of momentum is based on Newton's third law of motion, which states that every force has a reciprocating equal and opposite force. We will study in the next lecture here. What is the real life example of law of conservation of momentum? The thrust that you feel at the time of firing is one of the real life example. Now, what is the law of conservation of momentum? Obviously, as I have told, in case of our M1 into U1 equals to M2 into U2 equals to M1 V1 plus M2 V2. Now, what is this? M1, M2 are the masses of two bodies, U1, U2 are the initial velocities of the two bodies, and V1, V2 are the final velocities of the two bodies. Now, does friction affect the conservation of momentum? Yes, friction affects the momentum. As friction increases, momentum decreases. Now, according to second law of motion, the rate of change of momentum is directly proportional to the force applied. To the force applied. Okay. Next, let's solve this one. Before that, I am changing the ink color. Here, mass of the bullet. Mass of the bullet, that equals to 100 gram. If you change this into kg, then this will be 0.1 kg. Mass of the gun, that equals to 20 kg with a velocity 100 meter per second. So here, velocity of bullet, that equals to 100 meter per second. Now, we represent this using U and recoil velocity, recoil velocity of gun, that is V, and we have to find out this one. Okay, calculate the velocity of recoil of the gun. Now, first step, step 1, here before firing, just a minute. Before firing, the system, that means the gun bullet, here the system is the gun bullet is at rest. So therefore, initial momentum of the system, initial momentum of the system is 0. And final momentum of the system is how much? Final momentum of the system, that equals to momentum of bullet plus momentum of gun, right? Momentum of bullet plus momentum of gun. That means M into U, that is the momentum of bullet, plus momentum of gun, M into V. Okay, this is M bullet. What is our small m? and let we denote using capital M. So now we can write down mu plus mv. Sorry, this will be capital M v, that equals to 0.1 into 100 plus 20 into v. So that equals to 10 plus 20 v. Okay. So here, that is the final momentum of the system. This is the final momentum of the system. So I am doing here because the space is not so much huge. So let's step 2. Now you apply the law of conservation of momentum, where it has been said that final momentum that equals to initial momentum. Okay, that means 0 that equal to 10 plus 20 into v. So v equals to nothing but minus 10 divided by 20 or minus 5 meter per second. Okay, and this negative sign, it shown the direction of the recoil velocity of the gun, that is opposite to the direction of velocity of the bullet. This minus sign, here you can see one minus sign. This minus sign, it is shown that the direction of the recoil velocity of the gun is opposite to the direction of the velocity of the bullet, right? So the velocity, recoil velocity is the 5 meter per second, and this is the answer. Okay, and this is the answer. Let's see next one. Here, one iron sphere of mass 10 kg is dropped from a height 80 centimeter. So let's solve this one. Mass m, that is 10 kg, dropped from the height. Let distance s equals to 80 centimeter. That means 0.8 meter. Acceleration, that is 10 meter per second square. The downward acceleration of the ball is 10 meter per second square. Calculate the momentum transferred to the ground by the ball. Okay. From the law of motion, we know that v square minus u square, that equals to twice as. So v square minus 0, because initial velocity is 0. So that will be 2 into 10.8. That means 16. So v equals to root over of 16. So v equals to, this implies 4 meter per second. Okay. So momentum, now momentum of the sphere just before it touches the ground, that is our m into v, that means 10 kg into 4 meter per second. So that is 40 kg meter per second. Okay, this much. This is the moment. Now, this is the momentum of sphere. This is sphere just before it touches the ground. Another thing we have, that is on reaching the ground. So on reaching the ground, the iron sphere comes to rest, right? It will drop and that means it will come to rest. So its final momentum is 0. Okay. So according to law of conservation of momentum, momentum transferred to the ground that equals to momentum of sphere just before it comes to rest. That means 40 kg meter per second. So, but it is the momentum just before touching the ground. Just before touching the ground. Okay. Thank you. And next we will study third law of motion.